Good day. Today we are going to discuss context flow diagrams, CFD, and data flow diagrams, DFD. For a general introduction, we will discuss when to use these diagrams and their purpose in system analysis and design. A context flow diagram, CFD, is used at the beginning of system analysis to provide a high-level view of the system, showing its boundaries, external entities, and the flow of information between the system and its environment. A data flow diagram, DFD, is used to analyze and document how data enters, moves through, is processed, stored, and exits the system. In simple terms, the CFD shows the system's external interactions, while the DFD shows how data flows within the system. Let us repeat the overview of CFD and DFD. A context diagram, level 0 DFD, using gain and Sarsen notation, represents the entire system as a single central process that interacts with external entities, with labeled arrows showing the flow of data. A context flow diagram, context diagram, represents the whole system as a single process and shows the flow of data between the system and external users or other systems. Next, let us identify the CFD symbols. Please observe the symbols intended for a context flow diagram, CFD. Process, rounded rectangle, represents the entire system as a single process, usually labeled process 0.0. External entity, double square, represents a user, organization, or another system that sends data to or receives data from a system. Data flow, arrow shows the direction in which data moves between the system and external entities. Let us understand the core rules for drawing a CFD. A CFD shows the entire system as one single process. It displays external entities, such as users, organizations, or other systems. It shows data entering and leaving the system through data flows. It does not show internal processes or detailed data flows within the system. No data stores. Internal data stores are omitted because storage and other internal details are hidden at this level. Not every input data flow must have a corresponding output data flow. An input may be used internally without producing a direct output to an external entity. Another important rule is that the data flow arrow should be labeled with a noun or noun phrase because it represents data, not an action. Therefore, labels such as customer information, login credentials, order details, and payment information are correct because they identify the data being transferred. In contrast, labels such as submit order, process payment, update record, and send invoice are incorrect because they describe actions or processes rather than data. Let us proceed to an example of creating a context flow diagram, CFD. This time, carefully observe the information provided, particularly the input and output data flows, and how each external entity contributes to and interacts with a single system process. Remember that the CFD should represent the entire system as one process and should only show the data exchange between the system and its external entities. Based on the given input and output data, the following is the completed CFD diagram. Please observe that each data flow is labeled with a noun or noun phrase and represents the general data expected to be provided by or received by the external entities. Note that data store symbols are not used in a CFD because internal data storage is not shown at this level. The diagram contains a single process that represents the entire target system, using its logical or physical system name, the system that you're going to analyze and explore for design. Next, our question guidelines for identifying input and output data. How do we construct and identify the data to be used as input and output in a CFD? Let's use the following question guidelines. First, ask, what information does this external entity provide to the system? The answer represents the input data. Next, ask, what information does the system return to this external entity? The answer represents the output data. When naming the data, always use a noun or noun phrase because the data flow represents information, not an action. We should also ask, is this data crossing the system boundary? If the data moves between an external entity and the entire system process, then it belongs in the CFD. The simplest question to remember is what data goes into the system, and what data comes out of the system. Reminder, in a context flow diagram, CFD, data is considered to be crossing the system boundary when it moves between an external entity and the entire system process. Input, data flows from an external entity into the system. Output, data flows from the system to an external entity. Okay, let us now move on to the data flow diagram, DFD. A data flow diagram, DFD, is a graphical representation used to illustrate how data moves through a business information system. It shows how data enters the system, how it is processed, where it is stored, and where it goes as an output. A DFD represents the relationship between processes, data flows, data stores, and external entities, allowing us to understand where data comes from, how it is processed, where it is stored, and where it goes within the system. Let us identify the components of a data flow diagram, DFD. A DFD has four main components: process, external entity, data flow, and data store. These components may be represented differently depending on the notation used, such as Gain-Sarson or Jordan. Process. In Gain-Sarson notation, a process is represented by a rounded rectangle, while in Jordan notation, it is represented by a circle or bubble. A process represents an activity or function that transforms input data into output data. External entity. Both Gain-Sarson and Jordan represent an external entity using a rectangle. It represents a person, organization, or external system that sends data to or receives data from a system. Data flow. Both notations use an arrow to represent data flow. The arrow shows the movement of data between processes, external entities, and data stores. Data store. In Gain-Sarson notation, a data store is represented by an open-ended rectangle with two parallel lines, while in your notation, it is commonly represented by two horizontal parallel lines or an open-ended rectangle. A data store represents a location where data is stored and retrieved, such as a database or file. Please observe the symbols used in Gain-Sarson and Jordan notations, particularly the symbols for the external entity, data flow, process, and data store. Although both notations represent the same DFD components, their symbols may differ in appearance. Make sure to use the correct notation and symbols when creating your DFD. Now, let us identify the rules of data flow when creating a data flow diagram, DFD. Entities represent people, organizations, or other systems that interact with the system. They're considered outside the system because they are external to the information system, even though they may interact with its processes. Processes represent actions that transform or change data. Whenever a process occurs, it produces an output based on the input data and the rules applied. Typical processes include calculations, data sorting, validation, and the application of specific business rules. A process should be named using a verb, verb phrase, or simple sentence that clearly describes what the process does. A good process name generally follows a verb-object format, such as check availability or process payment. Data flows are represented by arrows and should be labeled with a noun or noun phrase that describes the meaning of the data being transferred. For example, customer information, order details, or payment information are appropriate data flow names. Data stores represent locations where data is stored and can be retrieved later. They commonly represent database tables, files, or spreadsheets, but they may also represent non-computerized storage, such as paper records, index cards, or other physical records. One of the important rules for developing a DFD is that every data flow must begin or end at a processing step. This is logical because data cannot be transformed or meaningfully changed without being processed by the system. Note that an entity cannot send data directly to another entity without some processing occurring between them. Data cannot move directly from an entity to a data store without being processed first. Data cannot move directly from a data store to an entity without being processed first. Data cannot move directly from one data store to another data store without being processed first. In simple terms, data must pass through a process when it moves between entities and data stores. The process represents the action that transforms, validates, updates, or otherwise handles the data. Next, please observe the correct and incorrect use of external entities in a data flow diagram, DFD. Pay close attention to how external entities interact with the system, and remember that data should not flow directly between two external entities without a process. Next, let us examine the correct and incorrect examples of combinations of data flow and process symbols in a data flow diagram, DFD. Pay close attention to how the data flow arrows connect to the process and ensure that each connection represents a valid movement of data into or out of the process. Another example is the correct and incorrect use of data store symbols in a data flow diagram, DFD. Please observe how data stores are properly connected to processes through data flow arrows. A data store should not connect directly to another data store or directly to an external entity without a process in between. The data store represents where data is stored, retrieved, or updated, while the process represents the action performed on that data. Another example is a mixed set of correct and incorrect uses of DFD symbols. Please carefully observe how the external entities, processes, data flows, and data stores are connected. Remember that data should flow through a process when moving between an external entity and a data store or between two data stores. Also, make sure that data flow arrows are labeled with nouns or noun phrases, while processes are labeled with verbs or verb-object phrases. This time, please observe the Gaines-Sarson DFD template and the proper construction of the data flow diagram. In particular, pay attention to when one process needs to be connected to another process. A process should be connected to another process only when there is a logical data dependency between them. For example, when the second process cannot perform its function without the output data from the first process. However, if two processes are independent and do not directly exchange data, they do not need to be connected simply because they appear next to each other in the diagram. The sequence of processes should be based on the actual data flow and system requirements, not merely on their visual order. When a connection between processes is necessary, clearly identify the relationship and data being exchanged in both logical and physical DFDs. The logical DFD should focus on what the system does and what data is exchanged, while the physical DFD should show how the processes are actually implemented, including the specific systems, applications, files, databases, or other physical components involved. Since we have mentioned logical and physical data flow diagrams, let us understand the difference between them. A data flow diagram, DFD, can be classified as either logical or physical, depending on what aspect of the system it describes. A logical DFD describes how the business operates and how data flows through the system to support business functions. The processes represent business activities or functions, while the data stores represent collections of data, regardless of how or where the data is physically stored. In simple terms, a logical DFD focuses on what the business does and how it controls its processes without focusing on the specific technology used. A physical DFD describes how the system is or will be implemented and how the current system operates in practice. The processes represent programs, program modules, or manual procedures, while the data stores represent physical files, databases, or manual records. A physical DFD may also show controls used for validating input data, retrieving records, ensuring successful completion of processes, and maintaining system security. In simple terms, the logical DFD focuses on what the system does, while the physical DFD focuses on how the system does it. The common features of logical and physical data flow diagrams, DFDs, can be understood by comparing what each model represents. A logical DFD shows how the business operates, with processes representing business activities and data stores representing collections of data, regardless of how the data is physically stored. It focuses on the business rules and controls that govern how activities are performed. In contrast, a physical DFD shows how the system is implemented or how the current system operates, with processes representing programs, program modules, and manual procedures. Its data stores represent physical files, databases, and manual files, such as master files and transaction files. A physical DFD also shows controls for validating input data, retrieving records, ensuring the successful completion of processes, and maintaining system security. In addition, when processes operate at different times, they may need to be connected through a data store to preserve the data between those processes. Overall, the logical DFD explains what the business does, while the physical DFD explains how those activities are implemented and performed. The following example illustrates the difference between logical data flow and physical data flow in a DFD. Please observe how the logical DFD focuses on the business activities and the data being processed, while the physical DFD shows how those activities are actually implemented, including specific programs, procedures, files, databases, or other physical components. The following is an example of a DFD using a logical concept. Please note that, for demonstration purposes, the customer external entity is repeated in the diagram. This is also acceptable in actual DFD construction, especially when creating DFDs based on different system modules, as repeating an external entity can help improve the readability and organization of the diagram. Please also analyze the next example, which presents a physical DFD. Observe how the logical processes and data flows are translated into their physical implementation, such as specific programs, program modules, procedures, files, or databases. To summarize, a logical DFD focuses on what the business does by describing its business processes, data inputs, outputs, and rules, without focusing on the technology used to perform those activities. The data flows may represent either manual or automated activities because the main focus is on the business process and the information being exchanged. On the other hand, a physical DFD focuses on how the system is actually implemented. It shows the specific people, hardware, software, databases, files, and procedures used to perform the processes. The physical data flow represents the actual implementation of the system, which may be manual, automated, or a combination of both. In simple terms, the logical DFD explains what the business does, while the physical DFD explains how the system performs it in the real environment. Now, let us discuss the data flow diagram, DFD, guidelines that should be followed when designing a DFD. A process should represent a single major function or module of the system. If a system contains different modules, such as student registration, grading, and payment, each major module can be represented as a separate process. When naming a process, use a verb plus noun phrase because the process describes an action performed on data. Examples include register student, calculate grades, and generate report. A process can connect to another process when data produced by one process is needed or used by another process. The connection must be represented by a data flow arrow, and the arrow must clearly identify the data being transferred. Examples of appropriate data flow names include student information, grade details, and payment information. Finally, processes should not be connected directly without a data flow label. Every connection between processes must use an arrow labeled with a noun or noun phrase that identifies the data being transferred. Avoid using simple lines or unlabeled connections because the DFD must clearly show what data is moving between processes. Next, let us continue with the data flow diagram, DFD guidelines. A process can read data from or write data to a data store. The data flow arrow should clearly indicate what data is being retrieved from or stored in the data store, such as student records or grade information. External entities should not connect directly to one another in a DFD. When data needs to be exchanged between two external entities, the data should pass through a system process so that the system can represent how the data is handled. Similarly, data stores should not connect directly to one another. A process must handle the movement or transformation of data between data stores. This ensures that the DFD clearly represents how data is processed within the system. As a general rule, a normal process should have at least one input and one output because a process transforms or handles data. However, there can be exceptions, such as source processes that primarily generate data and sink processes that primarily receive data, depending on the modeling approach. Finally, DFDs must remain balanced between different levels. The data entering and leaving a higher level DFD, such as a level 0 DFD, must remain consistent when that process is decomposed into lower level diagrams, such as level 1 or level 2 DFDs. In other words, decomposing a process should provide more detail without changing the overall input and output data flows defined at the higher level. Another important set of DFD guidelines concerns the organization, labeling, and readability of the diagram. External entities and data stores may be repeated on another page when necessary to improve readability, especially for large or modular DFDs. When repeating a symbol, use the same name and consistent labeling to clearly indicate that it represents the same external entity or data store. The diagram should also avoid crossing data flow lines whenever possible. Arrange the processes, entities, and data stores carefully to keep the diagram clear and easy to follow. If crossing lines cannot be avoided, appropriate connectors may be used to maintain readability. For data flow naming, always use a noun or noun phrase because a data flow represents information being transferred. Examples include student information, payment details, and grade report. Avoid using action words or verbs as data flow labels. Finally, processes should be numbered consistently to show their hierarchy and make the DFD easier to understand and reference. For example, processes can be numbered as 1.0 register student, 2.0 calculate grade, and 3.0 generate report. When a process is decomposed into a lower level DFD, its subprocesses can use corresponding numbers such as 1.1, 1.2, 1.3, and so on. Other guidelines for CFD and DFD. There is no fixed limit on the number of process symbols that can be used in a DFD module. The number of processes should depend on what is needed to clearly represent the functions of the system. However, if the diagram becomes too crowded or difficult to understand, it should be divided into smaller levels or separate pages. As a recommended guideline, a module should contain only the processes necessary to clearly represent that specific part of the system. Avoid adding unnecessary processes that do not contribute meaningful information to the diagram. Readability is also important. If a DFD becomes too complex or crowded, it can be decomposed into another level, such as level 1 or level 2, or divided across multiple pages. As a common practice, designers often use around 3 to 7 major processes per diagram to maintain readability, although this is not a strict requirement. Each process should represent a meaningful business function or system activity, rather than a very small step that makes the DFD unnecessarily detailed. The level of detail should be appropriate to the purpose of the diagram. For large systems, the DFD can also be organized by modules, such as a student registration module, grading module, or payment module. Each module may contain multiple related processes while still maintaining a clear and organized representation of the overall system. In a DFD, the data entering and leaving a higher level process must remain consistent when a process is decomposed into lower level diagrams. Keep the overall process and its external data flows at the higher level, while the lower levels provide more detailed subprocesses and data flows. Please carefully observe the example provided and compare the level 1 and level 2 DFDs. Notice how level 2 provides a more detailed breakdown of the processes as shown in level 1, while maintaining the same overall data inputs and outputs. The lower level diagram should add detail without changing the meaning or overall data flow established at the higher level. In addition, DFD processes should usually be arranged in a logical sequence that follows the real-world transaction flow. The purpose is not simply to list the processes, but to clearly show how data moves through the system and how one process supports another. For example, in a course enrollment system, a natural sequence could begin with maintain course information, which is performed by the registrar, followed by process course enrollment when a student enrolls in a course. The system then records the enrollment by storing the enrollment transaction and finally generates an enrollment confirmation that is provided to the student. It is also important to remember that not all data flows shown in a detailed DFD need to appear in the CFD context flow diagram. A CFD uses general data terms, such as student information or grade report, because it provides a high-level view of the entire system. In contrast, the Level 1 DFD provides more detail and may use specific data terms, such as enrollment records, enrollment details, assessment answers, and assessment results. This allows the lower-level DFD to show the specific data being processed while maintaining the overall data flow established in the CFD. Now, I have created an example of a physical DFD for a basic college grading system. Please carefully observe the diagram and understand that not all college grading systems will follow this exact process or structure. This is only an example based on the results of the system analysis and the requirements identified in the SRS. The physical DFD represents how the analyzed requirements are translated into an actual system flow, including the specific processes, data stores, users, and system components involved. The structure of the DFD should therefore be based on the actual SRS, interview results, and system analysis of the project being developed, rather than simply copying this example. Thank you for watching this tutorial. I hope you now understand the difference between CFD and DFD and have learned the proper construction of logical and physical DFDs. Make sure to master all the components, symbols, rules, and guidelines so that it will be easier to construct CFDs and DFDs correctly for both logical and physical system representations. For a better understanding of the system, you can also create DFDs using a module-based approach to clearly express how data flows between different system modules. Once again, thank you for watching and have a nice day.